I've given you one of my old lectures from Western Sydney, but I pitched that at such a level of mathematics that I thought I've got to soften to some extent. I didn't have time to do as much softening as I wanted to, so it's still going to be fairly hairy in various parts, but not as... You know, we've got a new module coming up in next year's Masters, an economic modelling module, which is going to teach nonlinear dynamics, complexity, multi-agent modelling, system dynamics, the work. So that a lot of what I'm covering now will be in that for next year.
We'll come back.
Pardon?
We'll come back.
It's going to be an interesting course. As I showed you last week, you look at how the neoclassicals think you should do economics, and it's all this micro-foundation stuff, which they themselves disprove without realising they've done it, but nonetheless that's them. And what I prefer to do is model from identities, and I think in that sense it captures what the post-Keynesian tradition has always been, realism. And the idea is to model, we are trying to get a realistic picture of the economy, and the question is how do you structure that realism? And you'll find all sorts of different attacks being taken at different times, but the fundamental thing comes down to starting from a realistic perspective. Well, there's nothing more realistic, I think, than starting from identities, things which are true by definition, and then you expand your expression of them. So what I showed you last week is just a very small beginning of that. I'll go a lot, in the next couple of lectures I'm going to go to a much more detailed model of the financial crisis than I've given you so far, but it's still working from identities. And what you get out of it is a complex system. And you get cycles which you can't understand in the way that, in the linear type of way that neoclassicals have done, let alone an equilibrium way, because the systems are non-equilibrium. So what I want to explain this week is the under the hood reason for why you get non-equilibrium behaviour coming out of systems like that. It's going to be boring to you because you've done all this stuff in great detail in maths before, but for some of you it's going to be a bit scary. Who knows what a Taylor series is? Okay, who doesn't know what a Taylor series is? Because he was known as Taylor. You don't?
Taylor series.
Oh, okay, so you've actually done it. All right,
I
okay.
don't know what one is.
Okay. And obviously in that case, who's heard of Eigenvalues? And who hasn't? Okay. So there are a few things that, again, I haven't had enough time to put it together properly, so this is going to be a pretty patchy lecture, but I'll go through a bit of that material, and then hopefully I'll get a chance next week to do a better backup and also go into the ways that I apply this modelling approach. Now, when you look at where the approach to economics in the sense of doing a dynamic model comes from that post-Keynesians have, Harrod was really the ultimate source. He's the first person to try to put a mathematical model of an unstable system into economics. And he wrote at the same time as Jagnar Frisch was developing the exogenous shocks approach to business cycles. And Frisch was one of the, I think it was there were two recipients of the first Nobel Prize, and he was one of them. I think the other was Hayek. And what he had was this proposition that you can explain what we see in the economy as a stable system subject to shocks, exogenous shocks. So you had the majority of oscillations that clearly be explained as free oscillations. The certain exterior impulses, something outside the economy hits the economy, and then there's oscillations coming out of the system. And he really called impulse problems and propagation problems in economics. Was the paper that he put that forward in the very first edition of the Journal of Econometrics, which he founded. And the whole proposition, you can see the model of the economy as a stable system subject to erratic shocks, as he says here, which then give you cyclical behaviour because of the way the damping of the damping of these external shocks by the stable system of the economy gives you cycles, and that was the whole approach that he developed. And that's, when you look at how econometrics is done today, it's still that fundamental belief is still there. And so the economy is stable, tending towards equilibrium, hit it with exogenous shocks, and then the pattern, the system's response to those shocks will give you cyclical behaviour. Harrod was the other way, was rejected this. And this is something which I think his philosophical stuff on this is more important than the mathematical stuff that he did ultimately. Harrod was one of these people who never developed anything more deeper than his first pass at something. So the papers he did back in the 1930s, when he wrote his 1960 book, there was really no progress in the mathematics. It was all extremely simple because he didn't have the background to take it any further. But he began in the right way. And he said that you look at how so the standard systems explain, you bring in a lag, and then you can get oscillations coming out of the lag you use. Okay, so the lag structure gives you a response to an oscillation to an external shock. And he said, first of all, there's doubt as to the nature of the trend on which this oscillation is explained. So this particular approach could explain oscillations around an equilibrium. It couldn't explain a trend. And I'll show that actually can. I haven't put that into this particular lecture, but I might add it, given that I didn't quite get the lecture finished. But in general, that's true, and particularly the model that became dominant in the 1940s, 50s and 60s, the trend was zero. So therefore, if you had just oscillations, you're oscillating around a zero equilibrium. Output zero. Negative output and positive output, okay, around an equilibrium of zero. So what Harrod argued instead is the trend of growth may itself generate forces making for oscillation. In other words, the cyclical imperative may come out of the growth imperative. They're not separate. And so he says it's an unnecessary tour de force to try to explain the trade cycle just by using lags. You should also be looking at the internal dynamics. So he said, let's abandon the assumption of the stability of equilibrium and introduce some destabilising factor into the model at the outset. Now that's Basomi summarising what Harrod did. If you want to see the global expert on Harrod, if you really want to do some further research, it's Daniel Basomi. Lovely guy, and somebody who's managed to become a leading academic without ever giving a lecture. He's been doing postdocs and all that sort of jazz all his career, but he's done the definitive coverage of Harrod. I've never seen anybody do anything even remotely as detailed than any other economist ever than what he's done on Harrod. The only possible person would be Schrafer on Ricardo in terms of the level of detail. And the Basomi's just reflected everything Harrod's ever written. It's a remarkable resource. So search for his name, you'll find all the detail on Harrod. Now, Harrod's starting point was to say that there are three propositions from which he begins. The first proposition was that income is the most important determinant of savings. So, and this is again, as you can see, the Keynes's logic here: investment determines savings. Income determines savings. He said the rate of increase of its income is an important determinant of its source of supply. So the growth of the economy generates where the supply of savings comes from. And he said demand is equal to supply. Hang on, there must be, either I've made a mistake in typing it in, or there's supply and supply. So supply of savings is the first, demand. That should be demand in the second. I'll check and see whether that's in the original. It's probably a mistake. I mentioned a mistake by me. So the second one is the demand determinant. So he said it's what you then bring together, he says, is a marriage of what's called the acceleration principle and the multiplier theory. And that the accelerator multiplier models became the mainstay of trade cycle models back in the 50s and 60s. So here's Harrod with his arguments here, and in fact it may be when I say sloppy, this is an old slide I've copied, so it might in fact be the fact he got the words wrong in the original. I'll need to check that. So that's the first thing. The level of income determines the supply of savings. So if saving is some function of the level of income. And then the rate of increase of income is determined that's demand for saving, because you want investment. So he said investment is some function of the rate of change of output. And then finally he said demand is equal to supply. So you equate the two. That sort of argument. Okay. Well, in driving what he called his fundamental equation, he does it a different way, but this is probably the easiest way to go about it. You start from this argument of identity between investment and savings. Again, this is a definitional thing. And by the way, one thing I wish to do in economics is eliminate the word savings from macroeconomics. It's an entirely misleading term. Then you divide both of them by outputs, so you haven't changed anything. And then you bring in the change in output over the change in output, so you still haven't affected anything. Rearrange it, and you get this expression here. And that has three components to it, what he calls the incremental capital to output ratio is the way he described that. So it's the level of investment divided by the change in output. Okay. Then he had the rate of change of the economy, delta y over y, or then partial y over y as I've got there. That's the growth rate of the economy, and that's the savings ratio. So that became his fundamental equation. Now, there's all sorts of problems. I can talk about this later, but I'll cover a few of them here. But mainly I'm just going to show you what the mechanics of this turn out to be. So he's got C, which he used as expression for the incremental capital output ratio, multiplied by G for the growth rate equals S, the savings rate. And then he said, well, there's three types of growth. He took actual growth, first of all. It's what you actually record. And then what he called the natural. Now, this is one case, again, I loathe the way economists of all persuasions abuse the language by using pejorative terms and calling them scientific. So there's nothing natural about that rate. Okay? But that's what he called the GN, the natural rate. And that's actually the maximum possible. That's like the natural rate of speed of your car is flat out with the accelerator strapped to the floorboards in fifth gear. Okay? I don't think it's particularly natural, but that's the way economists. The maximum natural rate is the natural rate, as he called it. Then he called the warranted growth rate, and that's the level that fulfills the expectations capitalists have that will lead them to doing exactly the same thing in a later year. So those are the terms he put together. And from that he derived what he called his instability principle. So the basic instability was these are the two main forms of the growth equation. The GN comes in to explain cyclical turning points. But if you have the warranted rate of growth is the ratio between the savings rate and the capital output ratio, the I-core, that leads to capitalists making exactly the same decisions in the future that they've made in the past. S over CR he called the actual growth rate. But he's got them both equal to S, remember. Okay, well, they're both that particular, just go back and take a look at it again. That equation, he's keeping this constant all the way through and saying the savings rate is a given. Not in terms of a constant, but that they're both equal on the other side. So if you have if actual growth is greater than the warranted growth rate, then the incremental capital output ratio will be less than the actual one that occurs. Now what that means is, and my best example here is imagine a shop that sells Coca-Cola, okay, and it's got a stock of bottles in the back that's 3 times the size of the daily sales. Okay, and that's the ratio it wants to maintain. Well, if it gets a higher level of sales than it wants, so growth is higher, that means it's got to reduce the stock it's got in the back room. So the stock goes from being 3 times to less than 3. So the response of the shopkeeper to the fact that they've got more sales than they thought is to invest more, to buy extra. You've got to increase the stock in the back room 3 times as much as the change in the daily sales. So that means that as well as the customers demanding more Coke, the shop then demands 3 times as much, and the demand for Coke skyrockets. Okay? And then that process leads to further growth, and you get an accelerating trend away. So in his argument here, you've got if the growth rate is greater than the warranted growth rate, then the actual increase in capital is less than the desired rate. So growth accelerates, and capitalists will then, and you'll get a runaway process until you hit the natural, which is the boundary he's got on the upper level. So that's what he called a knife. He didn't call it a knife edge himself, but he objected to people describing it as a knife edge, and if you look at how he describes it, it's a knife edge. So I think Harrod is an unreliable source about his own logic, but he says, this is the argument here, if the actual rate exceeds the warranted rate, then producers on balance will not feel they've produced or ordered too much. Let's see, they'll be running short of stocks. Okay? It's the same argument given about the Coca-Cola. So they feel they haven't produced the warranted amount, they've got to produce even more to be where they think they should be, and what you get is a runaway process. Now that's the basic logic. It didn't go particularly far. It's sort of starting to some extent from identities, but even there you can criticise him having exactly the same S in both cases, for example. But I want to talk about what neoclassicals did to it, because as usual that's the main story. In any heterodox area you get to learn, it's the neoclassicals who take it over and stuff it up. And again, it's our dear mate John Hicks, or JR as he used to call himself. John Hicks, I'd happily have a drink with. J.R. Hicks would be better off drowned at birth given what he did to economics. And that's why he actually abandoned his own name. So what he did was he supposedly wrote a review, which is just what he did with Keynes. The Keynes, Mr. Keynes and the Classics is supposed to be a book review. And it was actually his, when you read his later literature, I think I've covered this point with you, haven't I? That he repackaged a 1933 model of his as his interpretation of Keynes. And he admits the model that he used in that paper had no relation. But you could see elements of it in the general theory. But it was really repackaging a model of his from a 1933 paper that hadn't been particularly popular. And then that became the model that he called Keynesian. So that was one particular distortion. But he did the same thing here. So he ended up doing a review of Harrod to promulgate Harrod's ideas, but that's something that's utterly unlike anything Harrod actually argued. In fact, the exact opposite of what Harrod argued. So he said, first of all, you can't have an unstable system. He said Harrod welcomes the instability because he thinks it explains fluctuations we've seen in the real world. He said, but mathematical instability does not generate fluctuations. A mathematically unstable system does not fluctuate, it just breaks down. That is a mathematically false statement. Okay, it's true of a linear system, most linear systems, but it's untrue of mathematical systems in general. You've already built one yourselves last week that proved that. Okay? Very, very simply. That was his piece. And now here we go. Faced with this difficulty, I have been tempted to go beyond the ordinary functions of a reviewer. My God, I wish he was able to resist temptation. Because what he did was turn Harrod back into what Harrod was trying to get away from. So he said, we've got to bring in frictions, and that a lovely word again, that neoclassical concept of frictions, to give mathematical stability without sacrificing the instability argument on which the case depends. So we just use lags, which again is one of the things that I showed you earlier Harrod wanted to get rid of. And he said, and then this talk about Snikey, it is not generally realised. Mr. Harrod has certainly failed to realise it. Talk about a slap in the face for a fairly prominent colleague at the time. But the great function of lags is to impose just that measure of stability and to make the system determinate. So what he does, first of all, he converts Harrod's relationship into discrete form. So the form I've showed you beforehand, even though it's kludgy, was actually effectively continuous time. So that's the continuous time expression. And what Harrod did was say, well, growth is actually yn minus yn minus 1 over in. Okay, so we're in discrete time now. Then he said that C, the investment part of the model, looks decidedly queer. He says, it's not reasonable to assume that current investment should depend on the increment of output in the same period. Well, that's a reasonable statement. Okay? If you're going to talk about how long capitalists take to respond to investment, then there is going to be a time lag, and I'd be using a time constant in there, in a continuous time framework to do that. But he said investment should depend upon the increment of income in the preceding period. And now notice the next little line, and consumption upon the income of the preceding period. This is one of the reasons I'm a big critic of discrete time modelling in economics as well, because the period, what's the period? Period for investment? 1 year? 2 years? Okay. Period for consumption? 1 year? 2 years? Are you spending the money you earned last week or last year when you buy the cup of coffee? Okay. It's nonsense to lag them to the same extent, but that's exactly what he's doing. And there's a good reason why he did it. If he didn't lag consumption as well, he wouldn't have got cycles. Okay, so it's all a case of manipulating to get the result you want, rather than doing an honest growth out from the actual logic of the model. So here he's saying investment is some constant. Now he's got his C multiplied by the change in output in the preceding 2 years. Now I'm going to show you a problem with that in a moment, but that looks reasonable enough. This one is totally questionable, and that's my first reaction when I saw Harrod's work and was working on it in an essay for my master's, was that's nonsense. And then you do your equating of the whole lot. You say savings is equal to output at time t. So savings now is output now minus consumption now. You've now got expression for consumption now, and that's again why you had to bring that in to get the lag. And then you equate the two. Savings at time t equal to investment at time t. So you get this expression. And that became, when you reorganised it, you got a couple of expressions there in yt minus 1. So you play around a bit and you get yt equals 1 minus s plus c times yt minus 1 minus c times yt minus 2. Okay? And this reason that's important here is I'm partly explaining why Minsky failed to build a decent mathematical model of his hypothesis, because he tried to use this model as a foundation for his model of financial instability. And it's a lousy model. In fact, it's not even a model. It's an economic error disguised as a mathematical model. And I'll show you why in a moment. So that's the expression he's got. And you get cycles but no growth out of that. The equilibrium of that, when you try to say what value will be restored over time, you could get a positive value out of a difference equation. You could get a rising value or a diminishing value. In fact, the only value that solves this equation is 0. And then economists, to analyse this, use what's called the characteristic equation approach. Have any of you used that at all? And some of you passed, so some of you have done that. Have you done the matrix conversion approach as well? Converting an equation? Okay. There's an enormous error in using the characteristic equation approach that goes totally missed in this model. You expose it immediately when you do the matrix transformation. So the stuff I'm taking you through, the mathematical stuff later, is going to be slightly heavy, but there's a good reason for it, because when you look at these two approaches, one didn't reveal the problem and the other reveals the problem instantly. Okay. So Samuelson derived the same model, and you get these sorts of outputs. If you give a value of c of less than 1, then the cycles are going to diminish over time towards 0. If you give a value greater than 1, then the cycles explode over time. And if you give the value equal to 1, then you're going to get, actually this is much larger, you can see, if equal to 2, you get gigantic cycles, and then finally it collapses to massive negative. Okay? And there's a huge amount of literature discussing the properties of this model. And it's all a waste of time. But what it actually did was actually undermine dynamics in many ways. Economists thought this might be a way to go forward. And then it really led nowhere. Lots of complicated papers about the properties of this particular equation and people trying to generalise it, but it really, dynamics sort of got dropped as not particularly interesting. But there's an obvious mistake. Has anybody seen this before? Or this is a new to claim there's a mistake there. Okay. Well, let's see how they went about getting their answer. First of all, they took the characteristic equation. That is, if you have what's called a linear homogeneous differential equation, so all the terms, the variables are multiplied by constants rather than by each other. There's no nonlinearity in the structure of the economy. And when you subtract, when you put all the terms in the variable on one side, you get 0 on the other. There's no constant term driving it. So what you have is you put it in a form where you've got a times the differential, the second differential, plus b times the differential, plus c times the actual value of y equals to 0. That's the equation you're trying to solve. And the approach you take in general, this is the common story in mathematics, put something in that appears that you know solves it, make it something, they call this the ansatz, the German word just for a guess answer. You put in a term which you know has the properties of the differential here, because if you differentiate an exponential, you're going to get whatever it's multiplied by out the front. Okay? So let's just go through this. R is an unknown constant, but if you differentiate that, you got the differential, the second differential of r squared, e to the rt, that'll give you an r squared term. The first differential will give you an r term, and that's just going to be constant. So when you expand it out, you get a multiplied by r squared times e to the rt, plus b multiplied by r times e to the rt, plus c multiplied by e to the rt. Okay? Now we know that e to the rt is not 0. Okay? It's a non-zero term. The exponential, when you have an exponential to the minus infinity, you approach 0, but you never get infinity, you never get 0. So you can collect all your terms there, and you know straight away that that is not a 0, so you can actually just multiply both sides and cancel it out. And what you've got is a quadratic equation. So you turn this thing, which is hard to understand, into a quadratic which is easy to understand. And that's the basic procedure in mathematics in many ways. Take something which you can't understand, put it in terms that you do understand. Now, of course, we know that a quadratic has got 2 roots, so the solution is going to be a linear sum of the two. So you finally work out the solution is going to be minus b plus or minus b squared, the square root of b squared minus 4ac. So you get a term like this, and pardon me, and that will now this equation for a polynomial will give you the same behaviour as this equation for a set of a differential equation. So you converted a complicated thing in different equations to a mucky but simple thing in polynomials, and that's what's being done there. So the same approach applies to difference equations. So you have a linear homogeneous difference equation like this. Then you assume a solution where now rather than being e raised to the power of r times t, it's r raised to the power of t. You put that solution in there. So you make that substitution, that's going to give you an r squared term, that's going to give you an r term, that's going to give you a constant. So go through to the same sort of story. You get ar squared, a times r to the t plus 2, plus b times r to the t plus 1 times c times r to the t. Again, a number raised to a power is not going to be 0. So you collect your terms. R is the root of a simple quadratic. The solution is the sum of the two. So that's the basic procedure. Now rather than having e raised to a power, you've got the root itself raised to the power of t. So y at t is going to be equal to that expression. So you've solved the problem. Okay. Well, let's apply that to Hicks's model. So you start from this expression. So you've got y at t is 1 minus s plus c times y at t minus 1 minus c times y at t minus 2. Convert, so you just add constants, so you get y at t plus 2 and the t plus 1 and t. It's exactly the same thing. You've just changed all the bases by adding 1 year to each of them. So you get y t plus 2 minus 1 minus s plus c times y t minus 1 plus c times y t minus y t, and you assume a solution of y t is equal to r raised to a power of t. Substitute that in there. So you've now got r at t plus 2 plus all of this times rt plus 1, so c times rt. Collect your terms, and now you've got the root in this polynomial. Nice and simple. So you solve it as a quadratic, and that's what you finally get, minus the b, plus or minus, etc., etc. And I didn't animate that bit, I'm afraid, but you can just simply show a solution to this. You get two roots to the quadratic, and then you substitute for y, and you get this expression raised to the power of t plus the other expression with the difference term for the radical, and that's going to be a system. So you just explore that polynomial. Well, not polynomial, it's a. But you converted. You got rid of the differential equations. You're working with exponents. Now, if you use the mathematics technique, you know straight away there's a problem. So what they do is convert it into a matrix equation and solve using linear algebra around the behaviour of a matrix. So what you do is you take the highest order equation. So you've got this expression here. That's where we're starting from the same starting point. You convert to a first order system. What you do is you define what you want to get is what you can call a vector differential equation. ddt of x, where x has got two elements to it, is some matrix A multiplied by the value of x. Okay? So that's the expression. That's what they're aiming to do. So what you do is you rearrange it so you start with the highest term there. So you now say that the second order differential is going to be minus b multiplied by dy dt minus c times y divided by a. And that's just rearranging the equation so you've got it in terms of the second differential. Then you invent a new variable which is part of a vector. So you define x0 as y and x1 as the differential of x0, which is dy dt. So you've now got x0 and x1, which are two elements, the first and second element in a vector. And you're now saying dx, the differential of x1, since x1 is dy dx, then the differential of x1 is going to be d2y dx squared, which is this thing up here. Okay? So you can then say, well, having done that substitution, you've now can say this is minus b times dy dt, and dy dt is x1, minus c over a times y, and y is x0. So you've now got this expression saying the rate of change of x1 is minus b over a multiplied by the rate of change of x0 minus a constant times the value of x0. Looking messy overall, but now let's put that into matrix terms. So you know how to multiply a matrix, you multiply the rows by the columns. Okay, so you get 0 times x1, okay, plus 1 times x1 coming out of here, minus c over a times x0 minus b over x0 times x1. Now that's messy. It looks, it's a messy process to go through. But what it means is you can now say what's going to happen with this model using the properties of this matrix. And one thing which is essential for this to be a genuine model is you must be able to invert. You must not be able to invert the matrix. And this, I worked this out because I was doing maths at the same time I was doing my master's degree, and this is the technique the mathematicians were using. So I was doing an essay on Harrod and Hicks, and I thought I'd just, rather than use a characteristic equation, I'd go through the procedure I'd been taught to do a matrix conversion, and I got a result I didn't expect rather. So I've got a ddt of a vector x0 x1 is a matrix A times the value x0 x1. Now, so that will work. Somehow the matrix A has to be equivalent to 0, because an operation we were doing all the way through in the characteristic equation was taking out e raised to the power of r times t, or r raised to the power of t, and saying, well, we can cancel that out because we know that can't be 0. Okay. Similar sort of thing here. We have to be able to cancel out the matrix because in some sense it has to be equivalent to 0, or they can't cancel it out. I'll show you the logic here. So you start off by saying your solution is going to be, again, the same basic idea, constant multiplied by e raised to the power of r times t, where the constant is now a matrix. So if you differentiate that, you're going to get the differential of this constant multiplied by e to the rt. You're going to get r coming out the front again. You're going to get r multiplied by the identity matrix multiplied by x is equal to a times x. So I've just expanded out this term here using matrix rules. And the identity matrix is just, of course, ones on the diagonal, zeros everywhere else. Now, if you rearrange this following matrix algebra rules, to actually, first of all, you've got to take the a times x across the equal sign, saying r times I times x minus a times x is equal to 0. And that 0, by the way, is not a single 0, it's two zeros, okay, because you've got two equations being shown here in a matrix sense. Now, and therefore your 0, the 0 you're getting equal to, is a matrix full of zeros. Now, that expression only gives you non-trivial values for x if you can now rearrange this and show that you can have this thing somehow is like multiplying x by 0 to get 0. Okay? But if this thing is invertible, then your only answer is x is equal to 0. Okay? Now, there's a whole procedure for working out whether something can be inverted or not, but it's called the working out the determinant, and most of you have done that. So you want to have x multiplied by this being equal to 0 not being possible, because if that is possible, if you can actually multiply and take this across the other side, then somehow this can't be equal to 0. Okay? You can't divide something by 0 doing equations, so that must be impossible to do. Because if it is possible, then your only solution is x is equal to 0, and that's the trivial solution. In other words, it's saying you haven't got a model. Okay? If you can actually invert the matrix for one of these expressions, then you haven't got a model. That's saying you're asking a question which is saying, what can solve this? So the only way you can solve this is to make sure inputs are 0. Okay? It's not a model. And that is exactly Hicks's model, unfortunately. So let's apply it. So you start off in this expression. You then convert, well, x1 of t is yt, and x2 of t is x at 1 at t plus 1, which is y at t plus 1. x2, which is the second element in the matrix, at t plus 1 is y at t plus 2. So you've done those are the two conversions you're doing. There's x1 defined and then x2 defined, and you're then working through the conversion. So x2 at t plus 1 is y at t plus 2. Putting all the other terms on the other side, we then substitute for y at t plus 1, we have x1 at t plus 1, and for y at t we have x1 at t. Okay. Now that then gives you this expression, x1 at t plus 1, which is the dynamics we're trying to work out, is going to be a multiplied by x1 at t and x2 at t. And there's your matrix. Now you want this to be effectively equivalent to 0, so non-invertible. Okay? It's invertible. That's the inverse. So in other words, it's not a model. There's something wrong, something logically wrong with the model. Okay? And this, I published this in one location, a book chapter in Commerce, Complexity and Evolution. I submitted to this economic journal, and this is the way that I met Richard Goodwin by correspondence, because he was one of the referees who, in favour of it being published. Another guy blocked it because I hadn't quoted his articles on Harrod in the EJ, and the editor rejected it on the basis of the one person who was against it when Goodwin was enthusiastic about publishing it. And this is one thing, just as a bit of a warning to you in journals over time. I could interpret that as being rejecting a non-orthodox paper, which is part of it. But the reality is the journals are so overwhelmed by so many bloody submissions by academics, all following the publish or perish imperative, that the editors are looking for simple reasons to get rid of just to reject articles without even thinking about them. So even a trivial rejection, and this guy's rejection was trivial, and I looked at his book, he's lucky I didn't quote his book, and I would have trashed it. It was nonsense. But anyway, it got rejected. And the reason this happens, is a practical reason, is they simply want to stop thinking about them. So what that means is often the refereeing at the top journals is lousy. They actually want some lousy refereeing just to reduce the volume. But if you get the minor journals, I'll give it like a review of, let's take the review of Keynesian Economics, which is a brand new journal, or if you try the journal of, Review of Political Economy. Okay. I got far better refereeing out of those journals than I ever got out of a leading journal because they're trying to establish themselves. Okay. So the editor pays more attention to articles, the referees are better. So strangely enough, you'll often get better refereeing out of a low-quality journal, so-called, partly because of the post-Keynesian bias, but also because just the sheer volume, the bigger journals just want to have reasons to turn stuff down. Anyway, what it means here is there's something logically wrong with the model. And that is fairly easy to show because what you're actually doing to get the model is you'll create a lagged relation for actual savings. Now, he's claiming that savings are based on income last year. That's nonsense, but you can put up with it temporarily and say, okay, well, I think that's crazy, but if you say, let's say consumption is based on last year's output, okay, let's do that. That's not so bad. But what he's got for investment is not actual investment at all. It's desired investment. He's saying investment at time t is some constant multiplied by the change in output between yt minus 1 and yt minus 2. Now, actual investment is the change in capital stock. Okay, so actual investment is going to be capital at time t minus capital at time t minus 1. And then you can relate that to output by saying if there's a rough accelerator relationship between capital and output, then actual investment at time t is going to be V multiplied by the change yt minus 1. So he's not working with actual investment at all here. He's working with desired investment. Now, is there any theory of economics that says actual investment has to be equal to actual savings has to be equal to desired investment? Ain't no such model. Okay? So it's a nonsense model. And therefore, when you put a nonsense model into mathematical form, the only answer to the model is 0. Okay, anything realistic becomes made into nonsense. That's why it's got an equilibrium of 0. So the whole model's a waste of time. Now, I've done a bit of further work on that, and I might cover that, if you like, as an aside later on in the lecture. But the whole argument, the failure to get anything interesting out of this model wasn't the only reason, but it was a major reason why people thought that deterministic models just don't work. We've got to have stochastic models to generate cycles. So it wasn't the entire story, but it's a major part of the story as to why trade cycle theory and dynamics and economics in general didn't take over from the static way of thinking that economists have. So the failure was not because the dynamics is bad. The failure is because it wasn't a dynamic model at all. It wasn't even a bad model. It didn't even qualify as a bad model. Okay. It wasn't a model at all. It's a trivial mistake there. So you need a better approach, and that's where Goodwin is one of many. I mean, you've got plenty of Paleskian models and so on, as you know. I'm sticking with Goodwin because I think it's underdeveloped, and to me it's also, as I've realised, you can derive it from identities in the economy, and I think that's actually the right logical basis to start from. Start the identities and add your detail around that as you expand. So you can derive it, as I showed last week, either by starting from strictly true identities and putting them in a dynamic form, or you can work from a causal chain, as I did when you did the flowchart model with Minsky last week. You work a causal chain from capital to output to labour, etc., etc. You get exactly the same model. Now, it reduces to two equations, and I showed you that in the slides last week. I might take a break now because this is a fairly heavy little interlude coming up, so maybe it's time for coffee, a bit ahead of schedule, and then we'll come back and keep on rolling on this one. So, let's roll on. Okay, so when you look at, to explain this in detail, of course, in the slides in last week's lecture, and I'm not going to go through and repeat that today, so take a look back and see how it was derived. But basically you can get a logical statement for the rate of change of the employment rate, which reduces to, it's an identity at this stage, is saying that the rate of change of the employment rate is going to be the rate of real growth minus the sum of the population growth and technical change in labour productivity. And the wages share of output is going to, the rate of change of that's going to be real wage demands minus labour productivity. So those are absolutely true statements. So percentage rate of change of the employment rate of change of real output, that's your rate of labour productivity and population growth rates again. And then that's the percentage rate of change of wages, and that's the rate of change of, there's a wages share of output, and that's the rate of change of wages and the other term I've already explained. So that's at this stage we're working with a set of absolutely true identities. Now, you built it in Minsky last week by going around and doing that causal loop, but you get exactly the same model coming out of it. And of course you see that behaviour, which I'll just bring up and illustrate with this one. Slow it down a bit. Of cycles. Okay. Now this is a realistic model. It's not like Harrod's model where the cycles were fluctuations around an equilibrium of zero in a model that was actually a non-model. That's genuine cycles in a genuinely well-founded realistic model. So how do you understand where those cycles come from? And again, the same process as I've shown you beforehand, you've got to reduce it to a form you can actually understand. Because when you're looking at a nonlinear model, you've got the nonlinear terms interacting, and you can't really say what's going to happen out of multiplying those two together. You want to convert it into a polynomial type thing where you can understand polynomials, and you work with ratios, the lambda, and omega, rather than the absolute values of labour and capital and output as you had here. So if you look at this particular model as you've built it, then you have, that's the actual level of capital, the actual level of output, etc., etc. And you look at your equations, they're all done in those absolute terms. The idea is to reduce it to working in terms of the ratios, where you can actually have an equilibrium in the ratio and see what happens. So you start with these identities, and let's just expand this out and make the model now this time using the ratios, lambda and omega, rather than the absolute value. So you start from this definition here, and these two definitions, and let's make the simplest possible substitution. So linear relations again between output, capital, labour, etc., etc. Not because we believe them, but because it's the simplest possible way to start. And then you can add in reality of nonlinear relationships later. So your output rate of growth. Oh, pardon me. I better edit that before Matthias sees it. Sorry, Matthias. I didn't edit that properly. That should just be YR, not the Y hat R. Unfortunately, in this program, I can't get rid. I've just got to type over the top of it. There's no way to edit that out, so that's fixed up. Okay, so there's your rate of real growth, 1 over YR ddt of YR, and you say, let's make capital a linear function of the output, a linear function of the capital stock. So that's a simple relationship there. Let's go back to that. Okay. So I make that substitution. Now at this stage I'm making it into a model rather than being identity, because I'm using something which is debatable. Okay. I'm saying there's a linear relationship between capital and output. No, there isn't perfectly, but it's a starting point. So again, I've got to edit that mistake out here, but I substitute where I've got y, r, I substitute kr divided by v. Okay, so I've now got that's 1 over kr divided by v multiplied by the differential of kr divided by v. Well, v is a constant, so I can take it outside the differential. I know those two v's cancel. So I've converted the rate of growth of real output to the rate of growth of the capital stock. And that's when there's a linear relationship between the two. That makes eminent sense. They're both going to be growing at the same rate. I'll just fix up that equation there, pardon me. That mistake. So let's just fix that. So it should be y, not y hat down there. Okay. Now, the rate of change of capital, again, another assumption, again, so that's investment minus depreciation. Okay. So I'm going to have, so there's net, the rate of change of the real capital stock, that's why I'm using K subscript R there, is going to be net investment. I've stuck between, what do I use? I've got net and nominal as two words I want to use. They both start with N. I'm not quite certain how to get around that problem. Let's go back to here. So I say, okay, investment is the rate of change of capital stock. So I can now substitute, where's my mouse gone? Hang on. I can now substitute there and say that's now the net investment rate. So that lot there can be dropped out for this. And that's gross investment minus depreciation. Now depreciation I can make a linear function of the level of capital. Again, it can be more complicated than that, but that's a good starting point. So you say depreciation is some constant rate of the actual existing capital stock. And that tends to be, when you look at the empirical estimates, it's anywhere between 10% and 20% per annum, 0.1 and 0.2. Those ratios tend to be found empirically. And in the simple Goodwin model, gross investment here is profits. Okay? So I'm simply going to feed that in and just use that example just for simplicity. So I've got gross investment is equal to profits, which is output minus wages. Okay? So bring that inside here. So I'm now saying the rate of growth of output, but I'm trying to make a substitution for this term up here, is going to be 1 over kr ddt of kr, and I can substitute back in again v times y, and I'll show you why I do that in a moment. And the rate of change of capital stock, well, here I've got it being investment, which is real output minus wages, that's there, minus depreciation. So I've just expanded the whole set of expressions out. And now I've got a whole lot of stuff that can cancel. So you notice I've got YR here, so I can divide through by YR there. YR here, do the same thing. Here I'm going to have wage rate divided by total wages divided by output, so I'm going to get wages share of output coming out of the expression. So a few cancellations, I finally say that the rate of growth of the economy in real terms is 1 minus the wages share divided by the capital output ratio minus the depreciation rate. And that's substituted for this one up here. Okay? And then these two, if I'm going to have a constant rate of technical change and a constant rate of population growth, they're going to come out as the values of those constants, because this is A hat means 1 over AD ADT. Okay? So that's the rate of change of labour productivity. That's going to be equal to alpha. And this is 1 over ND dt, that's the population growth rate. I use beta for that, so that's going to be beta. So you've got your expression pretty rapidly out of that. So just by making those substitutions, your final equation for the rate of change of employment is 1 minus the wages share divided by capital output ratio, minus depreciation, and that term there in total is the rate of growth, okay, minus labour productivity, minus population growth. Okay. Same thing for the wages share. So you start from here, you simply want to expand this out. Because we know this one, that's the only term we don't have a definition for. So again, for the simplest possible expression, and this is what Goodwin did in his paper as well, let's just presume there's some linear Phillips curve. Now Phillips, and I actually saw somebody whose work Danny Blanchard quoted a paper that he referred me to. I don't know who actually wrote the original paper. But in it, it said this, it made a remarkable discovery that the Phillips curve is nonlinear. Remarkable discovery. It's in the bloody original paper. The whole idea of linear Phillips curves is a travesty. But that's what the neoclassicists have gone into. They don't read the original, so they rediscover what the original wrote 50 years after the original wrote it. Usual sort of story. But just for simplicity here, I'm using a linear, and of course in my own modelling I make it a nonlinear relationship. So I can now substitute this and say there's my rate of growth of wages share of output. It's going to be the reaction that capitalists have to a gap between the reaction that workers have to a gap between the actual employment rate and the rate at which they don't demand changes in wages. So as a pair of ordinary differential equations, we get this expression. I've now multiplied through by I have 1 over lambda d lambda t, multiplied through by the lambda, omega as well, and now you can see where the nonlinearity comes from. There is lambda multiplied by minus omega, and here you've got omega multiplied by lambda. And that's classic predator-prey structure. That's where it comes from. So it wasn't a case of Goodwin imposing predator, trying to find a match, like thinking predator-prey looks cool in biology, how can I patch this across to economics? It actually follows very logically from a set of very straight, simple definitions in capitalism of output and of employment and wages share of output. You get that same result coming out. So you can use the predator-prey models to explore this. And in Goodwin's inspiration was studying with a mathematical biologist and learning that this particular model existed, and that gave him the insight that actually turned Marx's ideas from 1867 into a proper model. Now when you look at what's happening, of course it's a neither stable nor an unstable model. So this is I've expressed the model now in Minsky, and I don't think have I copied it in there? I didn't. I'll do that before I forget. Hang on a second. I've lost my mouse, so this portable mouse, and I've got a terrible short-term memory. I've dropped the thing somewhere, and I haven't been able to find it, so I've got to use the mouse built into the keyboard here. It's not quite as good. Okay, let's see. Okay, so there's the Goodwin model. By accident I've loaded it. Okay, so what I've done here is I've built that equation using Minsky's notation. So if you look over here, the equations you'll see on the equation tab here exactly what I've just derived for you a moment ago. So just using Minsky's notation to do it. For the fun of it, I reversed it so it reads in the same direction that you read a set of differential equations. Here's the rate of change of lambda is lambda multiplied by 1 minus omega divided by v minus minus the sum of depreciation, change in labour productivity and population growth. It's exactly the same equation, so that's just writing it up in Minsky. And when you simulate, you get cyclical behaviour. Okay? That's the basic logic there. So I'll just actually hang on a second. Well, this is what I spend my time doing as I'm writing a presentation. I've got to go through. I do all this animation work, which I hope helps. I believe it does. I just hope I'm not being totally self-indulgent there. So I'll just actually move that forward, pardon me. This is what I didn't get a chance to do properly, but having had my unexpected dinner last night. Okay. So that'll give you an embedded version of the model inside there, and I'll whack it up on the website as well. So how do you explain that behaviour? How do you explain this dynamics, or mathematically interpret the dynamics? And that's where the same sort of process I've shown you for difference equations beforehand is applied here. So when you look at it, the equilibrium for the system is in the middle of that cycle there. You're looking at that behaviour. You can work out the equilibrium using those constants there, and that's the equilibrium value for omega, equilibrium level for lambda. But you never get there. You neither go towards it nor do you move away from it. So it's a neutral equilibrium, and the system will orbit that indefinitely. And that's where, as I said, Goodwin got his inspiration from learning about predator-prey models, but the same thing applies to those. So here's a model, a predator-prey model, saying the rate of change of fish populations is A multiplied by the fish population itself minus B times fish times sharks. And the basic logic there is just an intuitive statement from, I think it was Volterra, who, either Lotka or Volterra, I kept on forgetting who's the mathematician and who was the biologist. But that was the first intuition of the mathematician. But you can given this problem by a biologist saying we've got these strange numbers turning up in the ratio of sharks to fish in the catches that are coming ashore during the First World War in Italy. And how do we understand this strange behaviour? So the starting point for the mathematical model is saying, well, if you don't have any sharks, fish numbers will grow exponentially. And if you don't have any sharks, any fish, shark numbers will fall exponentially. And then what's the easiest way of bringing in interaction of two species? Well, you simply say if there are sharks, then some of the sharks are going to eat the fish. So there's some constant. The simplest way to show that is to say that the rate of growth of fish is some constant minus another constant times how many sharks there are, and that's how that equation is derived. I've expressed it. I'll just actually hang on. I'll just show you what I mean by putting it that way. Let's take a copy of those two equations. Hang on. All I've done is multiply across by the f. So if I delete these and delete the s here, then what I'm saying here, when you look at it this way, is the rate of growth of fish is some constant minus another constant how many sharks there are. The simplest possible way of bringing in the relationship between the sharks and the fish. Okay, you can have more complicated expressions if you have ideas of fish being able to hide in various areas, but that's just a straight, simple population relationship there. And the same for the sharks. And when you put it together, you get pardon me, I've stuffed that up. Let's just... Again, these are the things I would have liked to do last night, but I was too busy having an interesting time talking Australian politics. Okay. So you get a non-trivial equilibrium out of that, and how do you work that out? Well, again, that's simple. The equilibrium is where this is equal to 0 and that's equal to 0. So therefore this expression has to be equal to 0. You multiply through by the fish, and you get A has got to equal to B times S. So the equilibrium level of sharks is going to be A divided by B. Okay? And the same thing down here for sharks. So you have an expression for sharks. If you say, what's the equilibrium? Well, this expression has to be equal to 0. cancel out the s's, and you get f is going to be equal to c over d. So the intriguing thing in this particular model, one of the cute things about this predator-prey model, is the equilibrium for sharks depends upon the parameters you use for fish, and the equilibrium for fish depends upon the parameters you use for sharks. Okay? Classic thing of an interacting system. So that's your non-trivial equilibrium for the two. And is it stable? Well, the way you work at stability is say, imagine we're a slight distance away from this equilibrium, a really tiny distance away. Call that delta, distance away. And therefore you define a point z, which is the equilibrium plus a small deviation. That's what you're saying. Now the question is, what's going to happen to that small deviation over time? Will it grow or will it shrink? And then the model that determines that will tell you whether your equilibrium is stable or not. And here's where the Taylor series idea comes in, because your delta is going to be you're going to say you work out the characteristics of the equilibrium for a dynamic system by getting a tiny distance away from it, and then seeing whether you converge or diverge. And what you're going to get is a dynamic system in powers, when you use the Taylor series expansion, powers of this delta. And delta is small. Delta is going to be less than 1. Okay. So what's a half squared? Okay. You get 1 quarter. Okay. What's a half cubed? You get 1/8. Okay. So the nonlinear terms are going to be smaller and smaller and smaller, and therefore the linear term dominates. So to work out the stability of a nonlinear system around its equilibrium, you can work out the stability of the linear part and ignore the nonlinear ones because they're going to be smaller. Okay? So that's the fundamental trick here. So what you want to do is take this position and build a linear model of a deviation from equilibrium and see whether the linear model goes towards the equilibrium or not. So that's the basic procedure here. And so there's all sorts of ideas when linear algebra turn up in how you analyse nonlinear systems, which is why if you're going to learn dynamics properly, which we'll be teaching in that big modelling module next year, then you need to learn a bit of linear algebra as well as a bit of calculus. Now, as I've explained there, it's because when you're working where delta is less than 1, then the linear terms are much bigger than the nonlinear. So it's the characteristics of the linear part of the system that determines stability around the equilibrium, even when you've got a nonlinear model. And that's where the Taylor series expansion comes. You haven't done a Taylor series before. So who's not done work through how a Taylor series is derived? Who has worked? Okay, so at least a couple haven't. Okay, it's fairly simple because again, the trick. Hang on, my power's just gone off. Let's have a flat computer if I don't watch out for that. There we go. Pardon me. Okay. The simplest thing we know in mathematics in many ways is a polynomial. A is bx plus cx squared, etc., because we've done so much mathematics on it, and there's no nonlinear terms in a polynomial. Okay, you've got one constant times x, another constant times x squared, etc. So the route that economists, the mathematicians, take with almost all forms of data, the different with inherently cyclical forms of data, which is where Fourier transforms comes in. But you want to take, you've got a complicated model, convert it into a set of polynomials. Okay, that's the idea. And then the behaviour of the polynomials will be close enough to the behaviour of the system you derive it from. And then when you're working very, very close to the equilibrium of something, you can drop all the nonlinear terms because they're going to be so much smaller. Okay, so it's a way of getting approximately right, but the closer you get to equilibrium, the more correct that model is. Okay? So the way you get a function like this. So let's say function at t is equal to a0 plus a1 times x plus a2 times x squared, way out to a times an to the t to the n. So just presuming I've got some nonlinear function, I'm going to say it's approximately equal to all this stuff. There's going to be some error. Look, if you have, imagine trying to approximate sine with a polynomial. Okay, well you can, as long as you're willing to go to ridiculous numbers of powers. But if you stop at a certain point, ultimately your approximation is going to break down when you get a large distance from zero. So, but for most functions, you can fit them very close with a polynomial, and they'll deviate with higher terms. So you start from there, and all you've got to now work out is you've got f at t. T is your time step. So it's that's what you're feeding into the model: time at 1, time at 2, time at 3.5, etc. What you don't know is the value of these coefficients here: a0, a1, a2. So what you're trying to work out is how do you get the coefficients. And Taylor's simple idea was, well, let's just use differentiation. Because each time you differentiate a polynomial, you knock off one of the powers. And that's the simple idea behind a Taylor series. So if I know if I take the first, the f at t, if I say, what's f at t when t is 0, then all these terms are 0, and I only get a0. Okay. If I want to get what the a1 term is, if I differentiate this, then the differential of a constant is 0. Differential of this is going to be a1, and all these are going to be powers of 2, etc., etc. Second differential is going to expose this one, and that's the basic idea. So if I differentiate this, I get a1 coming out. So the first differential, a0 drops off. I get a1 times on its own, the t drops off. I'm going to get 2 times a2 because I'm differentiating a t squared with respect to t. I'm going to get 2 times t out of that. Here I'm going to get 3 times t minus 2, etc., etc. So having done that, I've now got a value I've got a1 coming out, okay? Then I've got the second differential, and I'm going to get 2 times a2 for the second. The third differential, I'm going to get 6 times a3, and on it goes. And as you go through the nth order differential, then your terms are going to involve a factor term. When if you have x to the 6th and you differentiate it, you're going to get 5 times x to the 5th. Okay? Then the next differential, you're going to have 5 times 4 times etc., etc. So you get a factorial term turning up, and that's the general term. The value of the nth coefficient is going to be n factorial multiplied by a to the n. So you're trying to work out this term here. What you find is it's going to be equal to the nth order differential of the model multiplied by n factorial. So that's the general way of replacing each of these a0s, a1s, a2s, a3s. You substitute that inside there, and that's going to an. Let's go back up again. An here is going to be equal to the nth factorial, nth differential of the equation divided by n factorial. And it sounds messy, and you don't. This is for a mathematician, you'd be required to reproduce this stuff. Okay? But for economics, it's just giving you background as to what's actually going on, what's the nuts and bolts, the engineering behind getting here. So f at 0, you feed in the value of t at 0, and a0 drops out. So your very first term is f a0 is the value of the function at 0. Then your second differential, take the second differential at 0. There are 2 series. There's the Taylor series and the Maclaurin series. I think the Maclaurin series works with t as equal to 0. The Maclaurin works at some other value, which you'd use when you've got something like log, which doesn't have a value at 0. But so the first process, f at 0 gives you a0. The first differential, also evaluated at 0, gives you a1. The second differential, evaluated at 0, gets you 2 times a2, etc., etc. And in general, you get this expression, your kth factor in this polynomial conversion of a nonlinear system is going to be equal to the kth factorial, the kth differential evaluated at 0 divided by k factorial. That's the basic rule behind a Taylor series. And this is all just to get the very first term, by the way. Okay? But when you look at when you're simulating a dynamic system, then you use generalizations of the Taylor series. So the Taylor series gives you a general statement. The process we're going here just looks at the first 2 terms, the constant plus the linear term. Okay. Things like the Runge-Kutta algorithm will use a 5th order Taylor series. There's all sorts of ways this turns up in mathematics in general. So on you go. You've now got the function of t, which is approximately equal to this polynomial. We now can say what the values of the parameters are for this polynomial. So it's f at 0 plus the first differential evaluated at 0 times t plus the second differential evaluated at 0 divided by 2 factorial, which is 2 multiplied by t squared, etc., etc. So we've now done that conversion. You've got the conversion terms. Now the linearized expression of that is just drop all this stuff and just stick with the first 2 terms. Okay? That's the linearized version. So your very first approximation to a function using the Taylor series is going to be a linear equation. Now, of course, the further you go from equilibrium, the less that is an accurate definition. So the first differential of sine, for example, is 1 plus xt, and that's a straight line that's going to diverge like crazy from sine. Okay, but you then add part of the second, and you'll get the curvature. Then it'll deviate, etc., etc. But when you're working just around the equilibrium for a nonlinear system, you can forget all the rest of the stuff and just work with the linearized version. So you've got to get to the linearized version. This gets very hairy, and for whom in the room am I repeating what they've already learnt at some stage? Quite a few, okay. For whom am I hitting the stuff you haven't seen before and it looks awful? Anybody?
I'm not that familiar with it.
Okay. Yeah. It's really, again, it's very important to understand the foundations of this stuff. Then you just basically pull it out of a trick box whenever you need it. So I'm just giving you the background, and I know I'm doing it too quickly, given the amount of time we have, but this is the reasons behind the procedure. So you start off with saying, here's your equation, your nonlinear equation, where x is a vector of values and f is a function of that vector, and you're evaluating it at the equilibrium. Since you're at equilibrium, the constant term you're working with is also going to be 0. Because if you're in equilibrium, there's no deviation from equilibrium. So we now define zt to be the difference between the current position and that equilibrium, and make z small so just the linear term dominates. Then what you get is z at t is equal to x at t minus x at 0. So I rearrange this and say x at t, which is what the dynamic system I'm trying to describe, is equal to z at t plus x at 0, and the differential of that is therefore the differential of the deviation plus the original value. That comes down to being just a function of x because the value of that equilibrium is 0. That's what you finally get. It's very messy notation, but I'll apply it for the model as we've done so far. That bit is 0 because the differential of x at 0 can now be expanded to this term, which is equal to the function of the function itself evaluated at that x0 position, which itself will be 0 because it's the equilibrium, plus a matrix of terms multiplied by the deviation we're analysing, plus the residual, which we're leaving off because it's all the nonlinear terms. Okay, so that's the linear bit. So we've reduced this. We're ignoring all the powers above that. We've reduced this equation to a term in the linear components only. So we've got a linear matrix here, and now I can say what are the characteristics of that A matrix to understand what's happening in the system. So what's actually going on? Imagine you've got this dynamic process here, and there's your equilibrium in the middle, and you want to work out, are you being forced away from the equilibrium or can you converge towards it? So you take a small distance apart, a small distance away from the equilibrium, and that's your dx dt, which you can reduce to being a linear equation of the deviation. So that's your Taylor expansion at that point, and you're now saying, is that going to go that way or is it going to move away? What's going to happen? So if this goes to 0 as t goes to infinity, then you've got a stable system because it'll return from here back to the equilibrium again. Okay? But if this goes positive, you've got an unstable equilibrium. So the question of whether you've got a stable equilibrium reduces to whether this A times Z grows or shrinks over time. Okay? So is that matrix expanding space or is it contracting space? And that comes down to its characteristics. So now we've got to say, what I've shown you beforehand was a Taylor series expansion for a nonlinear function in one dimension. Well, we've got a matrix expression here. So we have to get the equivalent of a Taylor expansion of a matrix, and that's the matrix of partial differentials, also evaluated at the same point. So if we have, what's this term going to be? It's going to be the function, the first differential of the function evaluated at the equilibrium, and there's two functions. F0 is the fish, and F1 is the sharks, looking at fish and sharks. Or when we go to looking at Goodwin, F1 is the employment rate, and F0 is the employment rate, and F1 is the wages share of output. So what you get is the matrix is going to be the partial differential of the function for fish here, divided by the fish numbers. This is going to be the function for fish divided by the shark, the differentiate with respect to the sharks, etc., etc. I should be using a partial term, though. Again, I didn't get a chance to fix that up. So you now have a new linear function like this, and if that's stable, then you know that the nonlinear system itself is stable. And that depends upon the sign of the real part of the dominant eigenvalue. And now, well, that's all. That sounds so. It's mumbo jumbo. Eigenvalues. Who can translate German for me here? Eigenvalue. Pardon? Own value. Yeah. Or principal value. It's just how a German mathematician did this stuff first. We're using German terms, but it just means a number that's a characteristic number that describes the properties of the matrix. That's all it comes down to. It sounds complicated. Eigenvalue. Okay. From an English point of view, it says, okay, what scalar number can I use to describe the behaviour of a matrix? That's what it comes down to. That's what's going on here. So if you get a scalar number that's greater than 0 out of this, your matrix is going to explode. And therefore you're going to have an unstable equilibrium. If you get a scalar number that's less than 0, your matrix is going to shrink space, and therefore your equilibrium is going to be stable. That's what it comes down to. And then also, you can get cyclical behaviour as well, because you're going to get square roots of negative numbers coming out of this. Complex numbers come out as a result of it. So you get this stability. You can understand the stability of a nonlinear system around its equilibrium by this process of linearising a small deviation and then seeing what happens to the matrix itself. So we're going to treat, with the fish and the predator-prey model I've shown you, C over D is the equilibrium number of fish, and A over B is the equal number of sharks. And you convert it into a polynomial around that point, and what you get is this expression. And I've got, so the x, which is fish and shark numbers, is going to be A times x0, which is the number of fish, minus B times x1, x0. Okay? And this is minus C times x1, C, the number of sharks, plus D times the number of fish times the number of sharks. That's your overall expression. Now we're going to define Z to be the difference between the current position, x at t, and at the equilibrium, which is x at 0, where you get x0, the first element is C over D, and x1, the second element is A over B. So what you get is this expression here. So I've got zt, that's the deviation. Then I can redefine xt this way, and I say the differential of xt becomes the function of z at t plus the equilibrium value itself. And now what I work out is those partial differentials, and that's exactly the same as the very first term in the Taylor series expansion. The first term in the Taylor series expansion is the differential of a single variable. Now I'm doing a differential for a pair of variables, so I get the matrix coming out of that. If there are two variables in the system, fish and sharks, get a 2 by 2 matrix of partial differentials. If I have a 3 variable system, I'm going to get a 3 by 3 matrix of partial differentials. That's why you've got that the Jacobian has that form. So having done that, let's see what happens. Again, I'm sorry I'm using deltas there rather than partial as I should be. But I've got the partial differential of the fish function with respect to the number of fish, the partial differential of the fish function with respect to the number of sharks. Okay? Now the partial differential of the sharks function with respect to the number of fish, partial differential of the shark function with respect to the number of sharks. So that's what's going on there. So let's just do that. Again, I've got to go through and edit all these deltas at some stage. But there's the differential with respect to the number of fish, with the fish function. So that's going to give me A minus B times x1. And then I'm going to feed in the values for x0, which is C over D, and x1, which is A over B. That's what all that notation means there. So again, the same story here. This is the differential of the fish function with respect to the number of sharks. That term is going to be 0 because there's no x1 there. This is going to be minus b times x0, and then I can feed in the value of x0, which is C over D. Okay. So this is the organ grinder stage of the work where you do all those reductions. And finally, that's first of all I've done the differentials here, and then I've got these are the values of the variables at the equilibrium I need to feed in. So I feed in x1 is equal to C over D. So x0 is equal to C over D, x1, which is the shark number, is A over B. So I get, there's my expansion for the first term in the matrix, second, third, fourth, and you work out this is a minus b multiplied by a over b. Well, that's 0. Ditto down here. And I get 2 terms on the off diagonal. Okay. Now, that is my final system. I'm now saying the deviations of the fish-shark system from equilibrium will change according to this dynamic. So the z will change as a multiplied by z. I've just noticed some of my notations again wrong. Further back I've got to fix up. I've got x there and I should have z. But this is the basic idea. You're getting a formula for the deviation. Is the deviation going to shrink to 0 or is it going to expand indefinitely? And the answer is no. Okay. This particular model, because your scalar part of it, your real part, depends upon these two. This is the imaginary part here. What I get out of this is cyclical behaviour. Have you all done imaginary numbers here, complex numbers? Okay, who hasn't done complex numbers? Okay, so I'm taking that for granted as well. When I taught in Western Sydney, I found my students hadn't learned complex numbers, so I was working with undergrads. So I had to teach them complex numbers as well as part of this lecture series, and that's why I'm a bit jumpy. I have to know what do I leave and what do I take out when I try to present to you guys. Anyway, having done all that, we guess, again, working out the stability, you do the same thing as we've done for the other models. You guess a solution for this differential equation, saying it's going to be e raised to some power multiplied by a constant. And because we've got a vector equation now, the constant's going to be a vector of numbers, not just a single scalar of numbers. So there's my expression, and I presume this is now a solution. So I've replaced the z in that expression by a times by the differential of this exponential here, and I now say, well, there's the dz dt. I'm presuming it's going to be a differential of e to the lambda times t multiplied by a constant, and that gives me lambda multiplied by e to the lambda times t times a constant. We've still got this equation here, dz dt equals a times z. So now saying this expression is equivalent to that expression. Now notice they've got two things in common. They've both got e to the lambda t. They've both got a vector. What differs is one has a scalar, lambda, and the other has a matrix, A. So somehow I've got to make an equivalence between the lambda and the A. Now that's the next stage. I then, following the laws of matrix mathematics, I subtract this from both sides, so I now get 0 over here. I've now got this lot minus that is equal to 0. And again, that's a vector of zeros. There's 2 zeros in that system because there are two elements in the equation, fish and sharks in the equation. So to actually do this operation, I have to multiply lambda by the identity matrix to convert across from a scalar equation to a vector equation. So I group all this stuff together, and I now get lambda multiplied by I minus a multiplied by e to the lambda t multiplied by v is equal to 0. And again, that's non-zero. I want this to be non-zero. I want a realistic value for the v. Okay, so this has to be somehow like 0. Okay, so exactly the same story as beforehand. The determinant of that matrix must be equal to 0, meaning I can't multiply both sides of the equation by it. If I can, I've got a non-model. So you get a quadratic coming out of that. So lambda times I minus a, the determinant of that is the determinant of this whole expression here. You then do your matrix mathematics and you get a expression in terms of lambda squared and a constant. And you say, what's the solution to lambda? Well, you find its solution is 0 plus or minus the square root of minus a times c. Now, because it's 0, what that's telling you is the magnitude of the gap between the equilibrium and your deviation is going to remain constant. Okay? Not going to change at all. So your deviation is going to be constant. The fact you've got a complex number...
It must be an orbit, not a spiral.
That's right, yeah. You can get systems with spirals in and spirals out. So
this is the orbit, because there is a... Okay.
Yeah, that's right, because you get this, the real part, which is determined by the diagonal mathematics, will give you... If that was a non-zero, then you'd have expansion or contraction, okay? But this term here gives you cyclical behaviour. So you're going to cycle around the equilibrium. And that's what you see in the problem. That's what you see in the model. That it just continues cycling around that system. The magnitude remains the same. It just cycles around it. So that's the behind the hood reason why you get that cyclical behaviour out of the Goodwin model. So if you're going to get convergence, that real part has to be less than 0. And therefore, e to the lambda times t will go towards zero because it's going towards minus infinity as time goes on, so you converge to the equilibrium. If you get the real part being greater than zero, then you get moved away from it. So the real part here is zero, so it neither converges nor diverges. So you can do your conversion and put this in terms of cosines and sines using the equivalence between exponentials and trigonometric terms. So you know, say it's going to be, your deviation is going to be 1, so it's going to remain constant in magnitude, multiplied by a constant times the cosine plus another constant times the sine of that expression. And that's as far as I got in putting that lecture together, courtesy of my long dinner with Kevin Rudd's brother last night. So that's why I'm sorry I said I didn't get as far as steam there. So I'll try to fill that lecture out. Couple of points. People asked, somebody's asking about what happens with solutions at higher orders. Like we solved a polynomial there, which was a quadratic. What happens when you try to solve say fifth or sixth order? And we know there's no solution to a polynomial above order 5, of or above order 5. So we tend to get fooled again by what we know. So if I, for example, tell MathCAD here to solve this particular expression for x, okay, let's do that, then it's going to tell me there's your familiar, minus b plus or minus the square root of b squared over 4ac, yada, yada, yada. What about if you have a polynomial, a third order polynomial? Ever seen the expression for that, the solution? Okay, I'll make this x cubed plus beta times x squared plus c times x, plus d. Doesn't look a lot more complicated, does it? Okay. The result's too large to display, okay, but it can be used subsequently. So I'm trying to get MathCAD, I'm trying to force it to show this to me.
That's our seagrass fish.
Yeah, the expression, the solution to that. I'll see if I can actually get it to show this, because I have got it to show it before. Let's see. So that's equal to 0. I'll try solving, if I should go for the other approach with the symbolics. Okay, variable, solve. There we go. Okay. Okay. So there's your expression, and you can see it doesn't fit on the screen. Okay, let's go over here a bit. Okay, now that's your solution for a third order. Okay, you want to see for fourth? Get the idea? No. It is actually. It's got a more technical. It's called a don't even bother. Okay, because it is only the quadratic is handleable. Even when you get to the third order, people start giving up. So, and that's with polynomials. That's just trying to solve a polynomial. Fourth order is just the computer. I don't think my computer could solve a fourth order. It might be able to. It certainly wouldn't display it. Fifth order, there is no solution. That's polynomials. And you get to dynamic systems where you're working in terms of differential equations. A solution for a first order is easy. A solution for a second order is complicated and cannot sometimes not be found. But a third order system of differential equations, nonlinear differential equations, there is no solution, period. That's what Poincaré proved back when he did the solution to the many-body problem back in 1899. So you get to the point where you simply have to say, how do you understand the system when we can't solve for it? Well, there's two things you can do. One, at low dimensionality, and 2 and 3 is low dimensionality. Then you can describe the characteristics of the equilibrium to some extent and describe the dynamics around it. Because when you're working in a third order system, you get a set of a polynomial expansion in the third order, and you can actually get a solution for that because we can get a solution for third order polynomial. So you can get an idea of the dynamics in a complicated system like that, but you certainly can't solve for it. Okay? So you could put a numerical simulation working out basins of attraction and so on. And I'm covering all that stuff in a book I started writing before I got the job here, which is my overall explanation for Minsky. So you see a few familiar elements to this particular chapter as well. And I should have used this as my source to get this lecture, but I just didn't have time. So I explain all the logic in terms of how a Taylor series expansion works. So here's, for example, looking at... Yeah?
So are you allowed to put this on this slide?
Oh yeah, I could do that for sure. I'll do that. It's unfinished. I mean, literally, I stopped halfway through a sentence. But if you can handle that, I'll work it up on study space. Okay, so it's basically all the preparatory stuff that I've covered in this lecture, but slightly better put together. So you're looking, there's sine, and I've got a linear, a third order, and a fifth order approximation to sine, and you can see the basic story. Close to the equilibrium, the linear dominates everything. After a certain point, the linear starts to deviate, so the third order becomes more accurate, but very rapidly loses accuracy, so the fifth order is more accurate, etc., etc. Okay? That's the idea of approximating a nonlinear system by converting it to a set of polynomials. I show all the deviations there, and this is all the procedures. I think I've got the deltas there. I've got to fix that up. You can see some of the equations I've edited that, and the others I haven't. Oh, that's deltas and partials. That's okay. Okay. So this is more mathematically correct. And then I go through the whole procedure I've shown you here. So that's a good idea. We'll put this up on study space. It's still incomplete. I haven't had the chance to finish it. But what's cute here is I applied this to the Lorentz model, which is the very first chaotic system. And again, it's an incredibly simple system. The beauty of the predator-prey model, the reason I used that to do the expansion initially rather than Goodwin's model, is the predator-prey model just has 4 constants and 2 variables. Okay? Well, the Lorentz model has got 3 constants and 3 variables. So it's extremely simple. And you can actually do the work that I've shown you here, the same basic idea. So here you're expressing it as a vector differential equation, and there are your outcomes of that vector differential equation. So we know that if you want to do the stability of the system around the equilibria, you'd take this expression here, this set of expressions, and you work out the partial differential of each of these equations with respect to the 3 variables in the system, and you get a matrix of partial differentials, which is what's shown here. And then you feed in the value at each of the equilibria. And I'm working with, I think I'm working with the 0 equilibrium here in this example. So I feed in the value of the 0, and I then get these terms. That's the matrix for the linearized version of Lorentz. Now, because there's 3 equilibria in the Lorentz model, then you've got 3 equilibria around which you need to do the expansion to describe the overall behaviour. And so there's a linearized version of Lorentz. Now, when you feed it in for the positive equilibrium, I feed these values in, and the 0 equilibrium and the negative, and I then get 3 polynomials, all in lambda cubed. And I can now describe those equilibria and the dynamics of the system around the equilibria. And what I get 3, my eigenvalues end up having, this is a stable, you can notice that's minus, because that's the real part of that particular set of eigenvalues is negative, so it's going to converge to equilibrium. But notice you've got you get 2 complex parts, and they've both got positive real parts as well. So the 3 eigenvalues you've got there, one negative, which is an attractor, and the other 2, which are cyclical, because they involve complex numbers, are also positive. Okay. So that's why it's called a strange attractor, because along one eigenvector, it attracts, along the other 2 it repels in a cyclical fashion. You do the same for the other equilibria, and you get a set of 3 equations for the positive equilibria, the 0 equilibria, and the negative equilibria in the Lorentz model. And then if you actually try to simulate that, this is the result of trying to simulate those models. So if you're working around the 0 equilibrium, which is here, your linearized version is a straight escape, okay, or a straight convergence. Pardon me. But that's not true, because we know it's going to be it'll cycle. When you do it around the other two, you get cyclical behaviour which is unstable, moves further away. We know that's not the case either. So you can see that the black pattern there is the actual the dynamics of the Lorenz model. The two sets of circles in the straight line are the linearized version of that model imposed on top of it. And you can see the linearized version completely distorts what the actual dynamics is. So at that point you've got to abandon linearization and work with the actual system. And that's the beauty of modern mathematics and engineering, that we've actually built technology that can enable us to simulate those things accurately. But linearization, let alone the belief that equilibrium is stable, fails when you start getting to these complex systems, which is why I'm trying to teach you very rapidly and today not particularly well the dynamics that's involved in that. Well, I'll go through Harrod, and this is partly one of my reason for having a very strong aversion to difference equations is multifaceted, but it began with this model because when I saw what Hicks had done to the model, first of all, there were total distortions about arguing that consumption is based upon income earned in the previous year. But then when I looked at the behaviour of the model, it was just a complete failure to get the time dynamics of the system right. So the way to fix up Hicks's model is say, well, actual investment is defined as the change in capital. Okay? And if you then say that there's a relation between capital and output, then I can feed that definition into the definition for investment, and I get investment at time t is going to be the accelerator times the change in output from time t and time t minus 1. Not this relationship at all. Okay? So that was the way that I could identify what the logical flaw in Hicks was. And then if you equate this expression to that expression for consumption, so you say if you have an income, savings equals investment expression fed in there, you finally get a growth relationship. Okay. So if you actually use the legitimate expression of ex post savings and ex post investment being equal to each other, then what you get out of it is a growth equation. Okay. So there was a logical mistake in what Hicks did in the first instance, and it escaped most economists because they didn't check the logic. Okay. The mathematics helps you identify there's got to be a problem. You find the problem is equating desired investment to actual savings. You correct it to equate actual savings to actual investment, you get a growth relationship. So that implies clearly we wasted a huge amount of time by not knowing the mathematics properly in doing this particular work. So what I then did is say, well, can we actually get something sensible out of Hicks even after all of that? And part of my argument was, and I'll show you how to do this in MathCAD in a moment, is I said, well, let's say that desired investment is, as Hicks used the expression, because desired investment is some constant multiplied by the change in output in the previous two periods. I then presume that capitalists carry out their investment desires, so actual investment becomes desired investment. So then say that capital at time t is capital at t minus 1 plus investment at time t minus 1. And investment at time t minus 1 will be what they desired to do. That's going to be c times y2 minus 3 minus y2 minus y2 minus y2 minus 3. And I then feed this all in, I finally get a third order difference equation. This is actually doing a realistic job of what Hicks should have done in the first case. In some ways I'm glad he didn't, because we would have been stuck with difference equations for even longer than we have been. But what you get out of that is an equation with cyclical growth. So I'll show you that in MathCAD. So I'm starting with saying investment at time t is actually defined as being capital at time t minus capital at time t minus 1. But desired investment is equal to, actual investment is equal to desired investment. The capitalists actually carry out their investment plans. And that's equal to some constant multiplied by change in output for time t minus 1 and time t minus 2. And then I can say capital at time t is equal to capital at time t minus 1. I just typed a 1 q by accident there. Yeah, I'll just fix it up in a second. I just noticed that. Can you read that at the back there, or should I make it larger? Yeah, okay, let's go for doubling the size. Okay, so investment is the change in capital stock. Desired investment is this lot. Let's say capitalists actually carry out their investment plans. Then I can expand this out to say that is equal to this also at t minus 1. So I just have to change the time script percentage here to make that y at t minus 2 and y t minus 3 now. That's now idt times t minus 1. And now if I say that there's some relationship between capital stock and output, hang on a second. So I say that, hang on, output at time t is capital at time t divided by the capital output ratio. Feed that in there. So I then get, that becomes k at t is v times y at t. So do that substitution. Pardon me. Working with this mouse can be a pain. Okay, that's better. Okay. So now let's substitute all that inside there. So this is now going to be v times y at t. This is going to be v at times yt minus 1. And this is going to be v times y. Well, I've already got yt minus 2 inside there. So I've now got this set of expressions for a different model. And let's then divide through by v. Come on, react. Okay. Okay. So divide through by v. So that's a third order difference equation, and that's logically sound. So let's now give some values for c and v. Let's say c is this is now the desired ratio of output to capital, which was partly part of Hicks's logic and part of Harrod's as well. Let's say the desired ratio is slightly higher than the actual ratio. So the actual capital output ratio is 3 and the desired ratio is 3.3. So let's just see what we get as a dynamic system out of that. I've got three values, yt minus 1, t minus 2 and t minus 3, that I need to work out yt. So if I say, for example, let's just now define those. I'll make up a matrix with 3 rows and say I have y at 0, y at 1 and y at 2, and make them equal to, hang on a sec, let's say that's 100, 103, 105. Actually, I'll make a bit of cyclical behavior. Let's go for 90, 98, 105. So I've got those are my first 3 values. And then let's say I'm going to have t going from, I'm not sure if I can start this well. I'll start with 2 out to 30, let's say, time periods. And now make this from a definitional statement into a actual equation. And I've got to make this, so let's make this t plus 3, t plus 2, that's t plus 2, that's t plus 1. Pardon?
What is V exactly?
Pardon? V is the capital output ratio, the actual ratio between capital and output. Okay. Okay. And C is the desired ratio, the ratio the capitalist would like to have. Hang on a second. I think I've stuffed this up a bit here. Yeah, hang on. Pardon? Pardon?
The second t plus 2 should be a t plus 1.
Yeah.
And the t plus 1 should be a t.
Yeah, okay. Now, so I'll actually make this 1 here. Let's see if that works. Okay, make it 0. I've done this before. I just haven't used MathCAD for a while, so I'm a bit out of practice. Okay, now let's just let's do a graph of the system here. So I'm going to have t and y of t here. Okay, so I get cyclical behaviour with growth coming out of that model, which is what we would have liked Hicks to derive decades ago, but he didn't. Now then say what happens if I change various values. So here I've got capitalists having a desired capital output ratio that's higher than the actual one. What about if they have one that's lower? Then you get conversion to an equilibrium over time, but still cyclical. And if it's the same, then you get linear cycles throughout time. So, to me it was just a tragedy that nobody corrected Hicks on this 40, 50, 60, what is it, how long ago now? 80 years ago or 70 years ago? So we got stuck with this nonsense model that dominated dynamics for all that time. And yet you could have put this together and got an interesting model if you'd actually had a bit of realism. And behind Hicks's apparent command of mathematics at the time was obfuscation. He just did a shell and P trick to use that C consumption depending upon the previous time period. Nobody checked him on that. Nobody challenged. Now that comes out of thinking in difference equations, because people think, oh, well, I've lagged investment, well, not lagged consumption. Yeah, but if you're going to do that, lag them by damn different numbers. Lag consumption by 2 weeks. Okay, so what you're spending is your money in your pocket 2 weeks ago, not the money in your pocket 1 year ago. Okay? And then you see the same thing happening in a lot of stock flow consistent modelling when people use discrete time. They lag by 1 year, everything, because they'll get algebraic loops coming out of what they've done if they don't lag. So they whack in a lag to do it, but the lag is a year, which doesn't make any sense at all. And then the real reason I have against using, even though I've generated a decent discrete time model out of this particular piece of work, the reason I'm against using discrete time in general is that if you actually do get an accurate model of the system that involves discrete time, then you're going to have a whole lot of different speed time lags. You're going to have consumption but lagged for 2 weeks, investment lagged for let's say for 70 weeks, and you'll have other elements, government behaviour lag by 113 weeks, etc., etc. And then if there's some change in the dynamics of the economy, so capitalists become more aggressive, you've got to rewrite all your difference equations, because you're going to have the investment based on, say, what happened 44 weeks ago. So you've got to redefine the entire structure of the model. Whereas if you work with continuous time, you'll have a set of time lags, and you simply change the parameters on the time lags. So in this sense, what you derive as the structure of the model when you're working in discrete time, if you do discrete time properly, has to turn up in the actual equations themselves, the structure of the equations. If you do continuous time properly, you just get different values of parameters, which you can easily alter. So to me, it's very important to get away from thinking in discrete time terms, rather than sticking with it, which is the unfortunate place we've ended up with in economics. So, and that's, I'm glad to say that I've got agreement on that front from Devram and Antoine, so we'll teach you some discrete time stuff. Discrete time matters when you start talking in terms of either one of two situations. Either you've got populations like red crabs, which all give birth on the same day as a survival strategy, and then it works under use discrete time. Or when you're using multi-agent, you're working up from discrete time. So, has anybody here used NetLogo yet? Anybody? I think I've got NetLogo installed here. Let's see. Hang on. Yep. Okay. So when you work in multi-agent terms, then it's obviously everything is discrete. If you're modelling population growth at the system dynamics level, you use continuous time. Okay? But if you're working in terms of a multi-agent model, then you have discrete time bursts and time sequences for births of each population and each agent giving birth at different times. So who has not seen NetLogo before? Wow. Okay. This is, I know it's not open source, but it is freeware, and it's a beautiful programming language for multi-agent modelling. And it brings up one interesting. We were just talking a bit about fish and sharks population in the discussion in the break, and I'll just bring up their version of the. Let's see where is it? Wolf sheep predation. So they use wolves and sheep rather than fish and sharks. This is Europe after all. Okay. So what this has, what NetLogo does, it's a beautiful multi-agent oriented programming language, and it's derived from an old language called Logo. Have you ever heard of Logo? Okay, some of you may have, school kids you may have got. Logo is designed as a way of teaching kids how to do programming. And so what do you do to make kids play with programming languages? You give them fun things like turtles that you put on the screen, and you tell them, okay, make the turtle move. Did you use it? You did use it.
Yeah.
Well, you've got some experience in this language, probably way back in there when you 6 and 7 year old part of your brain. Okay, you've got the background inside this stuff. And so what NetLogo does is take this beautiful little language to teach object-oriented programming and then apply it for multi-agent modelling. So in original Logo, the idea was to get kids to learn how to write a program. So, for example, they'd have the NetLogo would generate a screen, and there'd be a turtle on the screen, and the instruction would be move turtle 1. Okay, and you have to say left or right. So move turtle 1 right. Okay, and the turtle would move one set of screen coordinates to the right. Then you'd be told, why don't you tell the turtle to rotate? So turtle rotate 90. So the turtle pointing that way then rotates 90 degrees. Okay? And then the kids just say, now do that 4 times, and you draw a square. Okay, so it was a way of sucking kids into programming. Very, very nice language. So a guy called Minsky, I think his name is, thought it was a brilliant structure for multi-agent modelling as well, and built this overall environment. So this is like the screen that kids used to have for running their turtles around. Okay, and the programming language itself is really quite beautiful. This is the sort of stuff which I'm trying to be better in teaching than I would, and Tim Gooding, who's one of my PhD students, would be brilliant at teaching. But what it does is it uses very English language type structures. So I'll see if I can actually make that possible for you to see. Let's zoom a bit here. Larger control equals. Okay, let's go for that. So a few control equals. Okay. There's 3 elements to the model here. Notice the green stuff here. That's grass, obviously. But what the programming language does is describe what are called patches. So patches are little coordinates of the surface on which you move. So there might be like 100 patches defined there, 10 by 10, maybe 20 by 20. And then on the patches there are 2 types of turtles. And that's the part you've got to get used to, because all the primitives for objects in the language are called turtles. Okay? So you have to define different types of turtles. So what's being defined is there's a wolf turtle and a sheep turtle that's being defined. That's the part you've got to get your head around it. You're stuck with it. Okay, that's the history of where it came from. So you look at the code over here. Let's take a look at the code. You have breed, and a sheep is a particular type of turtle, and the wolf is a particular type of turtle. And turtles, notice this thing, turtles own. When you say turtles own something, you're deriving a characteristic that they have. So this is like a parameter for a dynamic system. So they have a property called energy. And to move, of course, that moving involves expending energy, and eating involves gaining energy, and then reproduction involves also using some energy, but it produces 3 turtles, which are little sheep, where there once before were just 2. And then on they go and they move around. So, and notice this, if grass, question mark, that's saying if we're actually modelling the grass in the system, then ask the patches. This is an instruction to each of the patches is also an object. Set your colour one of either green or brown, and then green or brown. Brown, of course, there's no grass there. Green, there is grass there. Okay? So the patches can either have grass or not have grass, and then you've got a countdown until such time as the grass runs. How does the grass, if you start from a bare patch, how long will it take the grass to grow there? and then you have a random regrowth of grass on that particular patch. Okay? So it looks strange when you look at it, but it's beautifully object-oriented. It's telling the objects what to do in different circumstances, and then you simulate the model. So the entire program, clear all, you get to blank the screen, ask the patches to set the colour to green. If there's grass, if there's grass is actually modelled, then the grass grows and the sheep eat it. And if it's false, then the sheep don't need to eat. They just stay alive without needing to eat grass. So the question mark turns on and off various elements of the system. So, and then it said, after it says set the default shape of sheep. So the sheep are given the shape of a sheep. They've got a little bitmap file that is an image of a sheep. And then you set their colour to white, their size, you label them, give them a random amount of energy and a random location somewhere inside that old set of patches, and then tell them to move about and try to find grass and eat the grass. And if they've got plenty of energy and there are two sheep that end up on the same patch, then they can reproduce, and then they all move from that patch, etc., etc. And the wolves in the meantime got a random amount of energy, and they go about trying to find sheep. And if they end up on the same patch, then they can eat the sheep that's there and get energy. But if they end up in a patch and there's no sheep there, then they've expended energy to get to the patch, and their energy level starts dropping. At a certain point, they can die. So that's all the logic there. I think it's a beautiful language. So let's see what happens when you run it. So I've set it up, and you notice there are random locations for a certain number of sheep and a certain number of wolves there, and the grass is off. Okay, so that means that's why it's entirely green. There's only two populations in this model. Okay, what I showed you with the predator-prey model, two populations, you get cycles. What do you think is going to happen here? You can't tell, can you? Okay, it's a complex system.
Probably they're all going to die off.
Pardon?
It all depends on how much wolves are out to move around.
Mm.
You know.
Explain your thinking there. Yeah.
If the wolves can go for several iterations with a certain amount of energy and keep going, then they will kill off the sheep.
Yeah.
If you set it that the wolves can only go, I don't know what that will be, but maybe twice or three times before they die, then you're likely to run into a stable system where, because the sheep will expand to the point where the wolves will be able to get them. Without dying, and then it will stabilise around that point. But as the sheep population retreats again, the wolves won't be able to catch them.
Yeah.
They won't die before they get there.
Let's watch.
In that case, you rented that thing because there were no locks to hide it.
Yeah, that's right. This is totally open. Ultimately, the wolves managed to eat all the sheep, and there ain't no sheep, so all the wolves starved to death. Okay. Well, let's actually now turn on grass. Isn't that a great expression? Turn on grass. Okay, set it up. So now notice some are blue and some are green. So there's some patches where the sheep go that they won't get any food. And of course, where the sheep go that they eat the grass, so the grass diminishes, but then the grass can regrow again. So off we go. Notice we now get cycles in the 3 dimensions. Okay. So the 3 interacting populations, where there's movement as well, will give you cyclical behaviour like we showed with 2 dimensions, where we ignored the fact that the fish had to eat something to stay alive.
Wolves aren't reproducing, are they?
Huh?
Wolves aren't reproducing.
Wolves are reproducing too. Oh, yeah, no, the wolves are allowed to have sex in this model. Yeah, okay. Well, that's.
It's all about how you vary the rate of grass regrowth.
Well, no. In fact, in this particular, once you have the 3 dimensions, this is one of the curious things about a dynamic system. If you have actually worked out an accurate statement of the logic of the system, then to some extent it'll work out its own parameters in an evolutionary sense. So if you have I've built a gigantic scale dynamic model of a 4 commodity economy that ended up being 41 nonlinear differential equations. And the first time I tried to simulate it, I was sure it would crash because the chance of me choosing a set of parameters that are actually in the stable range of this model is 0. And I ran it, and it worked. And the explanation was I'd got the dynamics basically right, and the system itself was nonlinear and unstable. Wherever I started it from, it would get to whatever the limit cycle was of the system. Continued behaving in a cyclical way, but it didn't break down. So similar things happening here. I haven't actually tried changing the parameters, but I've got a feeling that behaviour to be fairly robust to changes in the parameters, because it's describing it. You know, sheep do eat grass, wolves do eat sheep, and sheep do move, and grass does grow. You know, so yeah.
Kill half the wolves.
Yeah.
What does will it stay within its stable parameters, or return to them slowly, or will it explode out?
Going on Lotka-Volterra's original, the reason that the Lotka-Volterra stuff was derived in the first place was that the numbers, somebody was keeping records in Italy being the home of bureaucracy. Somebody was recording the catch data every day in Italian fishing villages, and also recording how many what they call salations, which the predators were being captured versus how many prey fish were being captured, and the ratio changed radically during the First World War. And he was trying to understand why this happened, because during the First World War lots of fishermen ceased being fishermen and became soldiers instead. So the amount of predation that we were doing of the fish and sharks diminished. And then we said, what was the impact of that? And then what happened was the number of sharks in the catch increased. Okay? So like you mentioned, if we brought a farmer, if you actually wanted to model fishermen here, then you'd make fish and sharks would be what you had, and the fishermen would be catching them indiscriminately. They wouldn't care whether they caught fish or sharks, they were catching both. Okay? If you have a farmer, then the farmer's going to try to kill the wolves, but not kill the fish, kill the sheep. So your dynamics of that is again describing a different type of dynamic, and you get different behaviour coming out of it. Yeah.
Oh, well, when the farmer kills the wolves, he's going to start killing the sheep himself, presumably. Right? Presumably he's doing it because he wants to take the sheep himself. Right?
Yeah, you'd have a certain rate of predation there as well. True.
It's not a problem. I'd say if you have Japanese sushi, they're not going to be really sharp. Well, obviously what happens if we kill off the world? At what point do the sheep...
Well, this is the sort of thing we want to teach in this course on economic modelling starting next year. You know, get you up to speed on this, because you haven't actually seen NetLogo before. Okay, see, I tend to forget how much experience I've had. So I haven't actually had a chance to do proper programming in NetLogo. Yeah.
My question here is like a normative one.
Yeah.
So we are aware now that like the economy moves in cycles.
Yep. Mm-hmm.
Now, should it be the task of, like, as a policy recommendation, so to say, should it be the task to reduce the cycle, or would you say let the cycle play out in its full dimensions? Like what?
This is where you get an interesting potential clash between what I talk about in modelling and what MMT does. Okay. I don't think the MMT crowd have got the degree of awareness of dynamic systems. Linwood, there's a particular guy in Kansas City that does not apply to. He knows his stuff well on trillion dynamics. But generally speaking, they talk about how to get a stable outcome, stabilise, no cycles, no unemployment, etc., etc. I don't think you can do that in a complex system. Okay, you might be able to find other ways to pay people money, which is where the job guarantee and things like that come in. But you're not going to get rid of the cyclical behaviour, and maybe to some extent, and this is the argument that people like Hayek make, maybe if you eliminate those cycles, you actually eliminate part of the dynamism of capitalism as well. Unintended consequences. So, yeah.
The outcome would be that kind of we need the destruction, like we have seen, like in the last cycle, like GDP losses of capital losses, like all this is like a necessary kind of price to pay, so to say, in order to advance economically in the long term, so to say. Like
yeah. I think there's difference between a tea party and burning down all the tea. Okay, and in that sense, if you look at Schumpeter's vision about cycles, he saw the cycles as playing an essential role.
Yeah.
Okay. Pardon me, look at Minsky, and Minsky argues, well, the cycles can lead to an accumulation of debt that causes a total crisis, which leads to complete systemic failure. Yeah. So I think Minsky's argument about stability was to say that a capitalist system is unstable, but to stabilise it doesn't mean eliminating cycles. It means keeping the cycles within bounds where the system can reproduce itself over time. And that then means, in my interpretation of that, is we have to keep the level of private debt down, because what actually causes the crises is an explosion in private debt. So if I in my model, if I confine private debt to a lower level than it reaches of its own volition, then I don't get a crisis. So a combination of things. Working out what the important elements are, so you've got to include debt in your dynamics in model of capitalism. Reduce the impact of cyclical behaviour on those who don't have any role in causing it, which is the workers, to some extent, okay. But enable the technologies to be created and destroyed. You want that creative destruction to occur. Yeah.
You said that energy doesn't recognise the dynamics. They're focused on buffer stocks, effectively. Buffer, as in Minsky's has his model is all about how you run your buffers down, get your return on equity higher or whatever, and that makes an unstable system. And it's not. The job guarantee has already had it. It was basically the rate that students had in his old age, where you could essentially live on
unemployment benefits were livable, yeah.
And did we have in that period lower levels of innovation?
Well, no, we had quite high levels.
In pop music, in large cultural events, we had far more innovation. I know people are contentious, but a lot of people agree that what distinguishes this period is how it's kind of incredible sort of retro mania, and we stopped being able to create new cultural things at the same rate that we were before. I know this is not clearly productive economic stuff, but that's my answer to the job guarantee, destroy it, and
oh no, it doesn't destroy the cycle. What I'd like to see the MMT people doing is building models of all the cycles you get out of those buffer stocks. You'd end up with complex cycles. We can model that, and that's just like Linwood, who's the system dynamics person in Kansas City, is quite capable of doing that. You've also got Mike Brzezinski, who's quite sympathetic, but also comes from my dynamic position rather than the MMT. I think we can meet in the middle, but you've got to admit your system's going to be cyclical. Yeah, but that's it. Let's go in the round a bit here. Pardon?
If you wanted to make that system stable, you have to introduce some sort of rationale or control. So wolves are only allowed to eat a certain amount of sheep are only allowed to eat a certain amount of grass. Right?
Yeah.
And that's kind of what you're saying in terms of like debt and stuff, right? You have to have systems in place where you say you're only allowed a certain amount of debt. Perhaps you're only allowed a certain amount of income, or you're only allowed a certain amount of,
or you treat other responses in the system that feed in.
So, but it would have to be that kind of thing. Right? There have to be some sort of rationing of the excesses, because what you've got in these systems is a sort of a desire to accumulate or eat or whatever, and then a mechanism by which that is stopped. And the mechanism by which that is stopped in these models is basically you eat so much of it that you go off and then you die, right? Yeah. So in order to stop that earlier, you've got to have a process of rationing where everybody goes, well actually there isn't enough to go round, so, or not if everybody goes through everything, so we have to control it more. That's exactly the opposite of what the neoliberal concept is, right?
Yeah, it is. That's a huge point. Firstly, why the neoliberals want to control the liability side of the balance sheet, because they think that's where the advantage is where you've got to control the asset side. You've got to put the constraint you want to impose keeps it stable has to happen on the asset side. You'll say you're only allowed to make so much of these assets.
Or you have to have a system which is triggered by what happens that's leading to a breakdown that stops that accumulating, which is like when I talk about the debt jubilee, I see that as being a necessary stage in getting us out of the crisis we're in right now. But if we have an economic which is aware of the importance of credit and the dangers of credit as well, you have an excessive rate of growth of credit triggering the government using its money to cancel private debt. So you have another system which comes in.
But there's massive moral hazard in that system. There's massive moral hazard in that system. You can't have a debt jubilee until it's all gone horribly wrong.
No,
if you have a debt jubilee, when it's okay, then it's like, okay, why am I not going to get it?
What I talk about is they call it a modern debt jubilee. and that would be where both savers and people who didn't have debt, who did have debt, both got a cash injection, but their debt had to be cancelled.
That's like going to dinner and saying at the end of the dinner we're all going to pay equal shares, right? Everybody then orders the most expensive thing on the menu, so the overall bill goes up. Do you know what I mean? If you say everybody gets that, whether you're good or bad, you get it. It still means that people are still motivated.
In other words, you can't leave the legal side of what you can order alone. And I agree. So what I've argued is you also have to have limits. The banks can't be allowed to lend on the basis of assets anymore. There's exclusive basis of lending. At the moment, it's all collateral based. So I would limit the amount that you lend for buying a property to some multiple of the income the property can generate. That's what I like to control on the menu. You can't order the most expensive item, as you're saying there. That would say that banks can only then say 10 times the income the asset will generate, which means that therefore there's no feedback loop that's going to cause asset prices to inflate.
Well, we're going to get back to wages.
Yeah, effectively.
That's what's going to drive.
Maybe I'm extracting again. So, I need that. So we are kind of saying that we isolate the effects of like the positive capitalism effects, the whole technology growth, the nice stuff basically, the culture, all this, from kind of the negative stuff where we have this pressure to accumulate whatever with this debt, that you would regulate, but kind of the good side you want to keep and the bad side you would kind of manage.
Yeah. Okay. I mean that's a form of ambition, but at the same time you go beyond that when you start talking about the climatic aspects of capitalism.
Yeah.
And
maybe I think you also go beyond this if you talk about some kind of social dimension that goes beyond like a bit what we have now.
Yeah.
I just wanted to ask, do you think that we ever had this kind of period where we could isolate, where we had this isolation you kind of imagine?
This, I hope we'll get time in the next week. Let's see if I can find the right presentation here. That'll do. Actually, I'm not sure I've got that correct graph. I'll just give me a chance to check the overall presentation here.
But that is the fundamental problem. Nature doesn't do bailouts. It's the fundamental problem we face, isn't it? You can always, whether you do it as a debt relief or whether you just take private debt onto the public balance sheet now, you can always keep the system going. And it's really a dynamic framework.
Yeah. This is a graph of private debt levels in America going back to 1834. The best I can do in terms of putting together a long-term data series using this is using the Federal Reserve's data from 1952 on. So we know that's a consistent definition over that period. This is the Census Bureau's definition from 1916 to 1970. And we can see they record a far higher level of debt here than the Federal Reserve does across an overlapping time period. When I do the R squared of the changes there is about 0.8. So it's quite a strong correlation. So I can actually use this structure saying, well, if the Federal Reserve had been around, that's what they would have seen as a level of private debt in the Great Depression. And this is another Census Bureau data series recording the loans of a fraction of American banks from 1834 through to 1970 as well. And that obviously recorded a lower level than the total level of debt. So putting the two together, I get this pattern as the pattern of private debt in America over the last virtually 2 centuries now. And there's been no point there where you've got stability out of the debt level. Okay? So in terms of that, the golden age we had in capitalism was this period. We had private debt between, in this America's case, as the Federal Reserve recorded, between 40 and 90% of GDP. But Minsky recorded the first big crisis coming in 1966. So in terms of historical experience, I see that range as being when we're in golden age conditions. Yeah.
Which was one of the only periods where wages really grew with productivity.
Yeah.
Because you didn't have to have debt-induced growth.
Yeah, and what I argue, that I haven't shown you the logic of this yet, but in fact, that basic Minsky model I've done, when I solve for the equilibrium of that, and I'll do that for next week's class, when I solve the equilibrium of that, the wages share is directly negatively related to the level of debt. or even though the model of capitalists doing the borrowing, capitalist wage share is set by the parameters in the system. So when you're near equilibrium, it fluctuates around the equilibrium. It's workers who pay for the rising level of debt. Yeah. And that's what you're seeing. They're getting less than productivity, consequently, over time. So yeah, and in fact, because of lower level of debt, there was more of the income share going to workers. Okay. And that's so.
But that's kind of the problematic I see, because this is also, if you plot this period, I think this what we have done in political economy, some guys do it, and this is also where accumulation goes down. Like where capital accumulation decreases, whereas wage share rises. So you have this conflict that then will enable or will kind of produce the effect that workers will take on debt.
Yeah.
This is kind of the contradiction.
It's in fact like the crisis without them taking on debt. So I need to believe it.
The terrifying takeaway from that graph.
Yeah.
The only corrective points are in 1860, a little bit in 1914, and then in 1948, rewards.
Exactly. And that's partly, I have a lot of disagreements with Piketty, but he said the same, but he said the same thing. It tends to be wars that wipe out the accumulation of capital. And then by doing it, what they also do is the debt levels fall, as we're seeing here, and with that effect coming through, which is where my causal link comes in, you then get a fairer distribution of income. War, I know. we don't want to solve our problems by killing each other on a grand scale.
Does your analysis suggest then that you can only have growth in the economy with growth in debt, and you can only have safe growth when we're coming from a point of very low debt?
Yeah, therefore you've got to get rid of debt on a regular basis, and we've got the capacity to do that because the state can create money as the banking system can. Or the other thing you go to is the Islamic approach around it. Because the reason this relationship exists is because there's a fixed rate of interest on the debt. Because whether you make a profit or not, you've got to pay the debt. With the Islamic system, what they do is say you don't take a debt position, you take an equity position, and therefore if the return goes down to the venture you've invested in or lent the money to, your return as a bank also goes down. So your risk share.
That's an interesting one though, because in the build-up to 07, there did start to become mortgage products, where the bank was taking an equity share in the property.
That's feeding the bubble. That's because again, that's all driven by the rising bubble.
But that's what you're saying, right? If someone if you say you can't lend money, you can only invest equity, right? So if the bank, if you're going to get a residential mortgage, and you're not going to let the bank say it's just a loan secured on the property, there has to be participation.
Which is why you can't have this. I've spoken with some people in Islamic finance and asked them what their main investment area was, and they said mortgages. And I said, in that case, do you realise you're feeding the bubble? Exactly the mechanism we're talking about. So it isn't just the case of saying all loans must be equity. You've also got to say where do you put limits on those leverages in there, and can you let banks make money out of rising asset prices? And the answer is you don't actually want rising asset prices compared to consumer prices. You want a rising stock of assets. You want to redirect our financial system so it generates more productive assets rather than price dynamics in the productive assets, which is what we actually get.
Here's another one for you then. An economy with a very large public housing sector would be quite isolated, quite insulated from this problem.
Yeah, and that's the German situation again. How many German students we got here? Okay. Tell me, I keep on being told, I still have. Is it true that when you rent a place in Germany, you're normally expected to provide a kitchen?
Yes, and the floor sometimes.
Pardon?
Often you're asked to bring your own floor.
Okay. Now that is such a dramatic institution difference.
Yeah,
literally.
Because in this country you have your tenancy is for 2 months, and then they can come out and want to take rent. In Germany you get much longer protection. You can't be thrown out. So you're expected when you arrive at a house, it's not the order. You're effectively a kind of form of leaseholder really. Long leaseholder. You'll often be expected to replace all the floors. You'll be there that long. And people want to do that, so you're allowed to do that. You have all your own kitchen. I had a friend who went to work in Munich, And every time it moves flat, you decide what you think. You don't know anything.
How often does you move back?
I mean, it depends on his first girlfriend. Maybe every 2 years.
You can't have a nutrition.
If you want to solve a young consumption problem, then I think you do. Depends on what you need. Yeah, but people will often bring their old bits and look more bits in it. It's all about lifestyle. In Germany, you go to shops and you get these guys with complete meal in bags and they go entire culture, something like that.
You buy the meal in a bag and then you sit on.
No, what I mean is that you literally, there's a stall where all the ingredients are laid out and the instructions how to make the food. And then you put it all in a basket. That's it really. And you take the card recipe to fill. You buy the meal, then you go and it's the same with their flats and everything. It's just it's how it's a completely different culture.
That's another thing.
Go off with that.
That illegal limit, as weird as it sounds, what it actually means is there hasn't been a housing bubble in Germany. And it isn't just because of the euro that's made.
All their banks had to get their subprime assets from outside Germany.
Effectively. In fact,
they did.
He told me this, one of my friends, Adair Turner, said that he actually enjoys provoking Germans by saying, so when are you going to get out of your credit-driven bubble here? And said, we don't have a credit-driven bubble. I said, yes, you do. Like the rest of Europe not doing it. So they actually said what's actually keeping your system going is the Ponzi scheme you're financing in the rest of Europe, not in Germany itself. And then, of course, what they're deriving all sorts of ideas about how one should manage the economy by the success of Germany. Well, one thing we can't all run export service, which is partly what they're saying. Why don't you all run export service like Reagan? In which case your export service will be zero.
Well, they're not running service, they're running a deficit of demand. So we need to get rid of the financial. They're so literally minded debt and shift guilt and change. So stop reporting demand to what point to a net demand reporting. And then they might listen to you.
Yeah, but we can import their legal system. And that's the legal rights that tenants have. If they existed in England, you'd have much less pressure to think, I've got to buy because I'm sick and tired of being pushed around by a landlord.
Yeah, we had that in the 70s, and that was one of the things that was...
Taking away from neoliberalism, let's make the situation worse, which again is why you've got to look at the economy as a complex system.
What do you do about growth and climate change? If you say that we need an economic system that generates an increase.